Now, I mentioned in a previous video that we can also write or use pressures for calculating equilibrium constant. So up here, these brackets stood for concentration, aka molarity. We can also write it for KPs or for pressures, sorry. So it would be KP instead of KC. They both are calculated the same way, but one can use pressures. Now that means that yes, they're related, but they're not going to be the exact same value. If you use pressure versus molarity, you would get different numbers, okay? Pressure and molarity are not the same thing, but they are related. So first of all, I'm going to show you how you would write a KP expression. Again, very similar, but instead of using brackets, we're going to use partial pressures. So KP, P stands for pressure. So in parentheses, I'm going to use partial pressures. Okay, so KP looks like this. I'd be like, okay, KP equals, again, products over reactants, but the way that we write partial pressures is like this. So capital P with a subscript CH4, okay? I'm going to put that in parentheses just to keep everything kind of controlled, I guess you could say. So it's the pressure of methane times the pressure of water over the pressure of carbon monoxide times the pressure of hydrogen gas cubed. Again, looks very similar to the one above, it's just pressures instead. So then I said that these are related, but they're not going to be the same value, well, at least not most of the time, because molarity is not the same thing as pressure. They are related, however. So the way that we can calculate one from the other, so like if I had the Kc, but I could only measure pressures in lab, then I could do Kp. Well, there is an equation that relates Kc to Kp, and that is this. Kp equals Kc times RT to the delta N. And I'll talk through what each of the variables means. This is on your equation sheet. You do not have to have it memorized by any means, okay? But this is the relationship between Kc and Kp. So if you have one, you can calculate the other. So what do all these variables stand for? Well, R is actually going to be our gas constant, and that's because we're trying to get to a pressures, and pressures really are only based on gases. So R is our gas constant. Okay. We usually use the 0.08 and that will actually make all of our units cancel out. That one is the liters, atmospheres, moles, and Kelvin. So we do have to be in liters, atmospheres, moles, and Kelvin. Moles and liters are what's in molarity. So that's actually going to work out and make our units cancel out. Temperature does have to be in Kelvin. Temp and Kelvin, because it is temperature dependent. I had said earlier that K can change with temperature. And finally, delta N. So delta N might look new to you. N does still stand for moles. So it is the change in moles. But the change in moles of what? Well, it is the difference between the moles of gas in the reactants versus the products. Okay, so delta N is like the product gas moles minus the reactant gas moles. Okay, so delta N right here, I'm going to do it for this reaction. Up here, if I wanted to calculate delta N, it's the number of gas moles in the products. Well, there's 1 mole of gas here. There's 1 mole of gas here. In the reactant side, there's 1 mole of gas here. And there's 3 moles of gas here. So that's 4. And so if I said calculate, if we needed to calculate delta N for this reaction, delta N example would be, this is 1 and 1. So products is 2 minus 4 is -2. So that power would be -2 if we were trying to do that calculation. Okay, so again, the 2 came from my products and the 4 came from my moles of reactants. And it is only based on gases specifically. All right, so we are going to do a practice with that really quick. I know it's not right after this, but if you can go to the next page where we've got some examples. Examples number 3 and 4 actually go with what we just did. So we're going to do those really quick. So example number 3 says, for the equilibrium, this reaction, 2 nitric oxides plus bromine gas makes 2 NOBr at 1000 K. The value of Kc is 1.3 times 10 to the negative second. What is the value of KP? All right, now sometimes reading these problems, you might be like, I don't know what to do. I don't know where to start. Well, look at your equation sheet. We literally have an equation that relates KC to KP. So I'm going to write out that equation really quick. Is KP equals KC times RT to the delta N. We just learned that, right? So I'm going to plug in what I know. Okay, so the value of KC is 1.3 times 10 to the negative second. Okay, I had told you to use the 0.08206. I'm not going to write out my units. I promise you they will work out. Temperature is in Kelvin, so times 1,000. And that goes to the delta N power. Now remember, delta N is the number of gas moles in the products minus the reactants. Well, there are 2 moles of this gas in the product, so it's going to be 2 minus, I got 2 nitric oxides and 1 bromine in the reactants, so that's 3. So that is going to be -1. So this is going to be to the -1 power. Okay, so make sure you do your order of operations correctly in your calculator. I would try it really quick, but your final answer for KP then should be 1.58 times 10 to the -4th. Okay, it is a simple plug and chug equation. All right. Finally, for example, number 4, I would like you to try to write these, the KC expression for this, and then the KP expression for this, just as good practice. Now, we will talk about this homogeneous and heterogeneous thing later. Actually, yeah, let's save this for the other video. So we're done.